All right, here's week 4 of pre-calculus. We have homework Tuesday, Wednesday. Thursday we're just doing a lesson, but there is no homework with it. And Friday's a quiz. Again, if you have any questions, here's my email. And let's get started. All right, we're starting a new chapter. 22A, we're going to do 2 sections. 22A is on experimental probability. Experimental probability is what did occur in an experiment. I should say the probability of what did occur. So maybe I flipped the coin 10 times. Flip coin 10 times. Now I should get 5 heads and 5 tails, but in my experiment, let's just say I had 7 heads and 3 tails. I didn't do anything wrong, but that was my experimental probability. The theoretical probability, which is actually section C, is the probability of what should occur. So the experimental probability would be 70% heads, 30% tails, where the theoretical probability would be 50% for both. All right, a few definitions or phrases. Number of trials is the total number of times the experiment repeated. So let's do an example while we're doing this. Let's put it up here. Let's say we flipped a cone 279 times. $183 landed on its side. And 96 times landed on its base. All right, so the total number of trials would be 279 in this problem. Outcomes are all the different results that could happen. The different results possible for one trial of the experiment. So in this case, there are 2 possible outcomes. It could land on its side or it could land on its base. Frequency is the number of times each occurred. Number of times that an outcome is observed. So again, in this problem, it was 183 times on its side, 96 times on its base. The relative frequency is the frequency of that outcome expressed as a fraction or a percentage. So some of these we had last chapter, some of these terms, so it's more review here. The experimental probability, therefore, would be equal to the relative frequency. So in this problem, the experimental probability of landing on its side would be 183 over 279. If it doesn't specify, you could leave it as a fraction as long as it's reduced. But usually probability, well, whatever, it doesn't matter. But I'm just going to make it a percentage here, 0.656. And then the experimental probability of landing on its base, I guess you could subtract that from 1, but you do have rounded answers, so it might be better to just figure it out, but you really could just subtract that previous answer from 1, 96 divided by 279. .344. And then one last note here. Even though we haven't talked about theoretical probability, how we get the experimental probability closer to the theoretical is to do more trials. All right, so the larger the number of trials, the more confident that the estimated probability will be accurate. But like I said, we could also say the closer it'll be to the theoretical, even though technically we haven't learned that yet. All right, so that's 22A. Like I said, we're doing 2 lessons on this first day. 22B is on sample space. Sometimes they use the universal set. So the set of all possible outcomes of an experiment. Like I said, also referred to as the universal set. Example. List the sample space of the possible outcomes for tossing a coin. Now, assuming it can't land on its side, usually we use a curly bracket. You don't have to, but when you have a group of answers, usually you want to use a curly bracket. Flipping a coin would either be heads or tails. Sample space of rolling a normal die. If they don't specify, we are always assuming it to be a 6-sided die. So if it says it's a 10-sided die, obviously it's 10 sides, but if it just says die or dice, we're talking about a 6-sided die, and die is singular for dice. So if we roll one die, we could get a 1, 2, 3, 4, 5, or 6. That would be the sample space. Use a two-dimensional grid to illustrate possible outcomes when two coins are tossed. Now, the two-dimensional grid isn't used as much in this problem, but in the next lesson, where the problem gets a little bit harder, more students are more apt to use the two-dimensional grid. For this one, it maybe isn't as needed, but it's good to see it with an easier problem. So we want to list all the outcomes when we flip two coins. So if we're making a two-dimensional grid, we have our X and Y axis. And it does the first coin, whatever, you could put it on the bottom or the side, that actually doesn't matter. Second coin, put on the y-axis here. So the first coin, we could either get heads or tails, and then obviously that's the same for the second coin, heads or tails. So when we cross-section them, where they intersect is a possible outcome. So in this case, there are 4 possible outcomes. This dot would be HH, and I'll use a curly bracket again, HT. Now that's different than TH, all right? The first coin was a tail, second coin was an H, and then the last scenario is tails, tails. These could be written in any order, but there are 4 different possibilities, not just 3, but there are 4 different possibilities there. Now, again, did we need to make a two-dimensional grid for this? Not really, but you'll see in a future example that it might be pretty helpful. All right, going with that same problem, I almost wish I had more room here. So listing the outcomes was the first problem. Second question, let's roll a normal die. Actually, no, my bad. A little rusty here. We don't need to do that one. We already did that one. All right, different example. Illustrate with a tree diagram the possible outcomes when doing the following. First problem, tossing 2 coins. All right, so sometimes IB will make you do a tree diagram or fill in what's missing on a tree diagram. All right, so tree diagram has branches, so on the first event, all right, so this would be one event. It could be heads or it could be tails. Okay, on the second one, it could be heads or again, it could be tails. And then we do the same thing down here, heads and tails. So the 4 possible outcomes, would be heads, 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 tails, tails, heads, tails, tails. And we get that just by tracing the branches. Tails, heads, and there's tails, tails. All right, again, we're going to illustrate with a tree diagram, drawing 2 marbles from a bag of red, green, and yellow. Now eventually we're going to do the probability of these, but right now we're just listing outcomes. So we don't even know how many red or how many green or how many yellow are in there, but we're just listing all the possible outcomes. So there could be 100 red, there could be 1 red marble in there. All right, so on the first pick, one of 3 things are going to happen. We're going to get a red, a green, or a yellow. What I found good to do when you're making a tree diagram with 3 is make 1 line going up, 1 going down, 1 going across. Just a thought. Then on the second pick, again, it's the same thing. Red, green, yellow. And then we repeat that. Wish I would add more room here. Red, green, yellow. Red, green, yellow. So if we list all these outcomes, we're going to have 9 of them. Red, 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 green, red, yellow, green, red, green, 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 yellow, yellow, red, yellow, green, yellow, yellow. How you make this better is I probably should have made it bigger. All right. But those are the 9 possible outcomes. And that is section B. Section C deals with theoretical probability. So I briefly talked about that about 5 minutes ago. Theoretical probability is the probability of what should occur. So again, when you go back to that tossing a coin 10 times, the experimental probability maybe was 7 heads and 3 tails, where the theoretical probability would be 50% heads, 50% tails. The formula for probability is the number of successes, or in this case A, over the total number of possible outcomes. Sometimes it's written like this: the probability of A over the number in the universal set. We don't have to write it like that, but that's sometimes how it's given. All right. Let's do an example here. Let's say we have a circle which is evenly divided into 8, and each section has a number in it. 1, 2, 3, 4, 5, 6, 7, 8. What is the chance or the probability of hitting a 5? Again, anytime in this chapter or any other chapters, we're assuming that it's random. All right, so like section 6 is not bigger than section 5. They're all evenly spaced. So the probability of 5, a success, would be 1 over the total number, and there are 8 choices. So the answer would be 1/8. We could change it to a decimal, 0.125. You could change it to a percentage, 12.5. But I'm just going to leave it as a reduced fraction. Okay. Let's try another one. What's the probability of a 6 or higher? Usually what I like to do is find the bottom number, the denominator, first. So the total outcomes is still 8. The successes would be 6 or higher. Well, that's 6, 7, and 8. That would be 3. So there are 3 numbers that are 6 or higher. So 3 out of 8 would be the answer to that. Okay. Here's a problem I've talked about a little bit. Now I'm actually going to write it down. Let's say we flip a coin 10 times and we got 7 heads and 3 tails. And they're going to ask, what is the theoretical probability? What is the experimental probability? There's a third question, but I'll just save that just for a little bit. All right, so again, the theoretical is what should occur. Well, what should occur is heads is 1/2 and tails is 1/2. Again, you can make those decimals or percentages. The experimental is what did occur, and that would be 7 out of 10 for heads and 3 out of 10 for tails. Now basically, maybe I should have made it a percentage, but it doesn't matter. But so right now the experimental is 70%, where the theoretical is only 50%. So then the question that they could ask is, why is the experimental far away from theoretical? And the second part of that question could be, how do you get them closer to each other? How get the theoretical, actually it'd probably be the other way around. How do we get the experimental, because the theoretical would never change. How do we get the experimental closer to the theoretical? So both questions kind of have the same answer. Why is the experimental far away from the theoretical? Didn't do enough trials. Not enough trials. We only did 10 trials. How do we get the experimental closer to the theoretical? Do more trials. Okay. Next example. Pick one, we'll say marble, from 3 green, 4 yellow, 5 blue. And again, we are always assuming it to be random. So I don't need to write random, and I probably won't anymore, but every problem we do, we are considered it to be random. Because if you could look in the bag, obviously the probability of picking a blue should be 100% unless you're colorblind. All right, so probability of picking green, again, is success over total. So we probably want to figure out the total immediately. So there are 3 plus 4 plus 5, 12 marbles. So that's the bottom number. The top number is the success. In this case, it would be 3. And we either need to reduce that fraction down, make it a decimal, or make it a percentage. So I'll just reduce it down to 1/4. Probability of green or yellow. So again, the denominator is still going to be 12. Green is 3, or means we're going to add. So 3 plus 4 is 7 out of 12, and that's already reduced. They could ask a question like, what's the probability of purple? And that would be 0 out of 12. And they're pretty lenient on how you write that. You could keep it like that. I think it's best to write it as 0 then. Or on the flip side, again, assuming these are all colors, what's the probability of picking a colored marble? Well, that would be 12 out of 12. And again, they're pretty lenient how you write that. I think the best way of writing that is 1. All probabilities have to be between 0 and 1. All right, let's do a different example. Roll a die. So again, we're assuming it to be 6-sided if they don't tell us otherwise. What's the probability of rolling a 6? Again, there are 6 outcomes. There is one time, one success where you can get a 6. So what is 1 out of 6? What's the probability of not 6? So that not, there's the not symbol. So again, there's 6 outcomes, and there are 5 numbers that are not a 6. So that would be 5, 6. Probability of a 1 or a 2. So again, 6 outcomes. You have a 1 in 6 chance of getting a 1. You have a 1 in 6 chance of getting a 2. So that's 2 out of 6, which reduces down to 1/3. Probability of not 1 nor 2. All right, so again, you can figure out all the other numbers. So 3, 4, 5, 6, that's 4 different numbers. And that reduces down to 2/3. Another way you could have done that is subtract the chance of it happening 1/3 from 1 to get 2/3, because that leads to this thing. These are what are called complementary events. And what that says is the probability of something occurring plus the probability of it not occurring has to equal 1. Next example. Here's where it might be more beneficial to use the two-dimensional grid. Use two-dimensional grid for tossing a coin and rolling a die. And then we're going to answer the following questions. What's the probability of tossing a head? Now they did tell us to make a grid, so before I answer that question, let's make the grid. So we got the X and Y axis. Again, it doesn't matter which one you put where. All right, whatever. I'll just put the die down here and the coin over here, but it could have been the other way around. So for the die, you can get a 1, 2, 3, 4, 5, or 6. For the coin, you can get a heads or a tails. So when we section these off, you will find that there are 12 outcomes. Wherever they intersect makes an outcome. Now they're just asking for the probability of tossing a head, so it really doesn't matter with the die. So we probably know that the answer is 1/2 because you're just flipping a coin, but you could get it from the grid also, because there are 12 possibilities and 6 of them are heads, and 6 out of 12 does reduce down to 1/2. But obviously we probably didn't need the grid to do this problem. What's the probability of a head and a 5? Right, that symbol means and. So and means they both need to occur. So again, the probability, there are 12 possibilities, I should say. How many of them have a tail and a 5? Well, the grid helps a little bit more here, and that would just be 1. So 1 out of 12. Now the question where I think the grid helps the most, this is the hardest problem, is the probability of a tail or a 5. Because what some people do is they know the bottom is 12, but they add basically they add the 6 possibilities for a tail and the 2 possibilities for the 5 to get 8. But you have to subtract 1, the one that repeats. All right. So there's a couple ways you can do this. You can just either not count it twice, or you did count it twice, but then you got to subtract 1. So you have 6 here, you have 2 here, but then we have to subtract what we counted twice, the overlapping. So this is 7 out of 12. So I think the diagram gives you a pretty good idea that there are 1, 2, 3, 4, 5, 6, 7. So the grid, I think, is helpful on this. So basically the